11.4 Area between curves. First, let's review area under the curve. Example, find the area under the curve of f of x is equal to sine of 0.5 pi x plus 1 from x equals -1 to x equals 7. The graph of our area under the curve is right here. It looks like 2 full periods of a sine curve. All of them are above 0 because we have the plus 1 in our f of x. And we're going from -1 to 7. To figure out the area, we want to find the area of each rectangle. Each rectangle looks like this. Each rectangle are very narrow. Well, we know that rectangle, the area is length times width, or in this case, we can say width times height, where the width is going to be delta x, except that we're not going to use delta here, we're just going to use dx, because we're going to take the limit as delta x becomes infinitesimally small. It's very, 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 very small. So the width is dx, which is very, very small. The height, well, we know that the height of our rectangle is given by fx, because our graph is as tall as fx. So that means that the height of the rectangle is fx. In other words, each rectangle has area dx times fx, which is of course just fx dx. That's why the total area of all the rectangles, we're taking the limit as the width of the rectangles goes to 0, is the integral from a to b, our two endpoints, of fx dx, which means for our problem, it's going to be from -1 to 7 of sine of 0.5 pi x plus 1 dx. Okay. For this lesson, for your homework and on the AP test, you can use a graphing calculator. So you can just go to wolframalpha.com and we can have them do the calculations for us. How do we do that? We just type integrate. Our function is sine of 0.5 times pi times x plus 1 from -1 to 7. Have them do the integral for us, and they get 8. Or from alpha gets 8. So the answer is 8. So here's the area, and the answer is 8. So the total area is 8, and of course the area of each of these individual regions will be 4 because there are 2 full sine curves. Okay. Next, to find area between curves, for example, later on we'll see a question like this. This is the area between two curves. We have a curve on top, a curve at the bottom. We want the area in between. We want to review the differences between integrals. We know that the differences between integrals is just the integral of the difference. So integral of f minus integral of g is just the integral of f minus g. This can be useful. For example, we have the integral from 2 to 5 of x squared plus e to the x squared dx minus the integral of 2 to 5 of 3x plus e to the x squared dx. Well, that's equal to, we can just subtract these. So it's the integral of 2 to 5 of x squared plus e to the x squared minus 3x plus e to the x squared. This is useful because we don't really know how to integrate e to the x squared. But as it turns out, they cancel anyway when we subtract. So this is really just equal to the integral from 2 to 5 of x squared minus 3x. This one we know we can do the integral manually. But again, we can just go to Wolfram Alpha. We'll practice using Wolfram Alpha. We're integrating x squared minus 3x from 2 to 5. Okay. And we get 7.5. And that's it. Okay. Our integral is actually negative from 0 to 3, but that's okay. Because adding a negative number and subtracting mean the same thing. Okay. There are a lot of questions on the AP test about area between curves. So we'll be looking at 2 examples, and your homework will also be problems from the AP test. Example 1. Let R be the shaded region bounded by the graphs y equals square root of x and y equals e to the negative 3x, and the vertical line x equals 1 as shown in the figure above. We want to find the area of R. Y to the square root of x we know looks like this. So the top line is y equals square root of x. The bottom line is y equals e to the negative 3x. Since square root of x is on top, e to the negative 3x is on the bottom. The square root of x is larger in this region where x is less than 1. We are finding the area. We must be finding the area of the integral from a to b of square root of x minus e to the negative 3x dx. Okay. Well, what are our integrands? Our limits of integration. On the right hand side is 1 because we're bounded by the vertical line x equals 1. Vertical means up down, horizontal means left right. Okay. So b is really just 1. Okay. But what is a? A is where square root of x and e to the negative 3x intersect. It's this point of intersection. That's point A. The problem is, where's A? Well, at A, given that they intersect, they're the same. That means that square root of x must be equal to e to the negative 3x. On the AP test, you're allowed to use a graphing calculator to solve this. So we'll go to Wolfram Alpha again. Let's go there again. We know that square root of x, we can just write sqrt of parentheses x is equal to e to the exponent negative 3x. Have the calculator online do it for us. And we find that the point of intersection is about 0.2387. On the AP test, it's a good idea to keep about 4 digits. 0.2387. You don't have to round if you don't want to on the AP test. Okay. So that's why our area then has to be the integral from 0.2387 to 1 of square root of x minus e to the negative 3x dx. Again, we can use our Wolfram Alpha, our calculator, to solve this integral for us. What we're really concerned about is knowing how to set up the integral. So we're integrating square root of x minus e to the negative 3x from 0.2387 to 1. And the calculator gives us 0.4426. Okay. And that's the area between the. Example 2. Let R be the region in the first and second quadrants bounded above by the graph of y equals 20 over 1 plus x squared and below by the horizontal line y equals 2. This one, they're not giving us the graph, and we don't really need it. By the way, first and second quadrants, just a review of terminology. This is the first quadrant, it's the top right. Second quadrant, top left. Third quadrant, bottom left. Fourth quadrant, bottom right. First in quadrants means that y is always equal to 0. Greater than or equal to 0, yep. So without a graph, what can we do? Well, it says bounded above by the graph of y equals 20 over 1 plus x squared. So that means that whatever that is, 20 over 1 plus x squared is on top. And below by the line y equals 2. So y equals 2 is on the bottom. And we're looking for the area between these two lines. So that means that the area has to be our function 20 over 1 plus x squared minus 2. Because 20 over 1 plus x squared is on top, 2 is on the bottom, dx. And we're integrating from a to b again. The problem is we don't know what a and b are. What are a and b? Okay, a and b are the points where the two are equal. Because we know that at some point we have this enclosed region. So at some point, 20 over 1 plus x squared must equal to 2. And there are 2 points where this is true. In other words, that's where 20 over 1 plus x squared must equal 2. Okay. We can use Wolfram Alpha to solve it for us. Again, divide by 1. Again, the goal for this problem is not to test you on the algebra, but to test you on whether you understand how to set up the integral. Okay, 20 over 1 plus x squared equals 2. The calculator tells us that x equals negative 3 and 3. Okay. So we get x equals negative 3 and x equals 3. So that means that a is negative 3 and b is 3. So to integrate, it's going to be the integral of negative 3 to 3 of 20 over 1 plus x squared minus 2 dx. Again, they expect us to use our graphing calculators, so we use Wolfram Alpha to solve this. Back to Wolfram Alpha, we'll integrate 20 over 1 plus x squared minus 2 from negative 3 to 3. And we get about 37.962. 37.962. And that's it. That's the area between 20 over 1 plus x squared and 2. So really, finding the area between curves just means finding the difference between two definite integrals. The key is we gotta figure out where our limits of integration are, a and b, which is usually just setting the two functions equal.